Okay, so thank you, Yash, for the lovely introduction. I want to start out by saying, thank you to the organizers, and also thank you to Vienna for being so wonderful. I mean, this is a really lovely place to be, and I feel very honored to be here. And I'm really grateful, so thank you for the chance to speak here and talk about this. Okay, so I have my phone is loudly clicking instead of silently clicking, so there we go. I gave this same talk at the Swiss Map Institute. So for people who saw that talk, I apologize that it's the same talk. I mean, there's some minor edits to the slides, but basically the same. We have some new stuff, but I guess following Richard's talk, the paper that this is on is coming imminently to the archive. I don't know what imminently means, sometime fairly soon. We had these results, slightly less than a year ago. And then we've tried to rewrite them to make them to pull out the finiteness properties. And this has been, the paper's been rewritten. It's much better, but we failed to pull out the higher finiteness properties. So somehow it's an exercise in failure to make a nicer paper, but okay, the paper's twice as long at least and says the same content. So, we'll see. Anyway, so coming in imminently. So here are my collaborators. Jim Belk, Francesco Mantucci, and Matt Zaremski. And it's a really fantastic group. It's so much fun to work with these people. So, think of them. I'm just a voice for the group. So, okay, so this is an outline. As you see, it's a pretty busy talk, right? There's a lot of things to go over. But if you find that the train is somehow pulled out of the station and you were still on the platform somewhere, just wait for the next part because it'll basically start from scratch. And so, there's every reason if you feel like something's happened that is confusing, you'll be able to get on to the next stop and it'll be okay again, except maybe the very last section where a miracle occurs, right? So, okay, so anyway, we're going to be talking about the Boone-Higman conjecture today. And so we really have to, before we even get into what is the Boone-Higman conjecture, I need to give you some background. And of course, like many people here are group theorists, right? So people probably know this for the large part, but okay, so here's a finitely presented group, and Dehn, this is obviously a translation, in 1911, says that the general discontinuous group is given by n generators and m relations between them as defined by Dijk in this Mathematischen paper. The general theory of groups defined in this way at present appears very undeveloped in the infinite case. And here there are above all three fundamental problems whose solution is very difficult and which will not be possible without a penetrating study of the subject. Now, you have to take into account that at this time, we didn't know formally what an algorithm was, right? So there was maybe a sense of what it meant to say that you had a procedure that terminated and would give you an answer, but this really hadn't been formulated, right? So so this is a very sort of insightful thing to go along with this sort of Hilbert problem. So the Hilbert program. So anyway, the identity problem, Dehn says, or it's now called the word problem, an element of the group is given as a product of the generators, and one is required to give a method whereby it may be decided in a finite number of steps whether this element is the identity or not. So here is actually a definition of an algorithm, right? Here's a method which will decide in a finite number of steps whether or not something happens. Now, we all know at this point that a lot of questions are only semi-decidable. You can get an answer on one half of the question, but your algorithm might run forever if the answer is actually the other half of the question. And in fact, many groups have this property. So, okay, so here are some key word problem results. There's been many, I'm only going to talk about a few. So there's this theorem by Novikov in 1955 and independently by Boone in 1958. There exists a finitely presented group G with a non-solvable word problem, okay? And, but then comes 1974, the Boone-Higman theorem. A finitely generated group G has solvable word problem if and only if it embeds in a simple subgroup of a finitely presented group. And one of the big mysteries of this theorem was they couldn't get it directly into a simple finitely presented group, but it wasn't really very clear why, right? They could get it into this simple subgroup of a finitely presented group, and it just seemed a bit extraneous that they had to have this extra layer. Okay, and so this is sort of one of the things. Now, in that paper by Boone and Higman, they make a comment about this really nice conference that happened in Irving. And Richard Thompson was having some discussion, and he was very interested in the word problem for groups as well. And actually, one of the reasons that V was created was to help him understand some attack on the word problem. And so he understood that you wanted to embed things into simple groups. And so he made a comment in the conference. It remained to Richard Thompson to note, this is in 1969, in his oral presentation of the Mackenzie-Thompson at the 1969 Irving Conference, that a finitely presented simple group has a soluble word problem. And this comment apparently triggered Boone and Higman to start really thinking about this. And then they made obviously a lot of progress. And then there's a theorem in 1974. But already there's evidence that they had the Boone-Higman conjecture back in 1973 because Boone gave some talk where he mentions it. So, okay, so what's the background for that? Well, Richard Thompson's comment was already well known in the Soviet bloc. So Kuznetsov in 1958 has a really short paper where he's talking about simple algebras. And anyway, you can extract from that paper that a finitely presented simple group G has solved a word problem. And the idea of it, okay, I mean, I'm just going to give the proof, although the paper, you can't find this proof directly in the paper, okay? So let G equal XR be a simple finite presentation of this non-trivial group. So G is simple, finite presented, non-trivial, and there's this presentation. And let W be some finite word in the generators and their inverse letters. And then build another group H, whose presentation is the same set of generators, the same set of relations, but you add the relation, you add W as a relation. Okay, and now one process that you can do is you can enumerate the consequences of a relator, right? You start with the empty word, and you can take whatever your present word is, and you can either insert a canceling pair somewhere in it, or you can insert a relator somewhere in it, or the inverse of a relator, or a rotation of the relator. Okay, so there's finite list of things that you can insert wherever you want in that word, and this is a consequence. And in that word that you now have, you might see some relator that you can collapse, or maybe there's a canceling pair or whatever, and then you can do that process. So you can just algorithmically build a tree of consequences, and you can see words that are going to be trivial. And if you organize that algorithm properly, every word which represents the identity will eventually appear. Okay, so what that means is that you can run this algorithm in parallel in the group G and the group H. And so in G, you find all the consequences of the relators. If W is a consequence of the relators in G, then it will eventually appear as a consequence of the relators in G, and then you'll know that the word is trivial. Okay, but if it's not, so that algorithm is running and maybe it's not producing an answer. Simultaneously, you're running the same algorithm in H, but for H, you're checking if all the generators appear. If one of the generators is equal to the identity, it will eventually show up as a consequence. And so if all of the generators of H are identity, then of course H is a trivial group. Okay, now we know that G is simple, so one of these two things is going to happen in finite time. Right, and so this is a decision process that gets both sides of the question. All right, so okay, I said 1974, but I could have said 1973. So there's the conjecture of Boone-Higman: a finitely generated group has solved a word problem if and only if it embeds in a finitely presented simple group. And so it's kind of a technical question. You know, can we get from just being a finitely presented? Can we get from just being a finitely generated simple subgroup and all the way to it's actually, you know, a finitely presented simple group? Okay, and so yeah.
You know that the group is given by a finite presentation, and it's simple. Size does it not the group is trivial?
Well, all the generators will appear as consequences of the relations.
Well, if it's trivial, you will discover it. But
yeah, but if it's not trivial, you know, I guess you know, you can't really do this process of you know, maybe you try for each generator building in each. I don't know. I haven't thought about it. Maybe there's an easy trivial.
James, do you have an easy answer?
I'm pretty sure the question's on that overflow somewhere. I can't remember.
No. I have done insufficient research on that overflow to immediately answer your question. Okay, so
Thank you. Okay, so anyway, so what is our theorem? What we're talking about today? Every hyperbolic group embeds an infinitely presented simple group, and this is the result that this talk is about. But I think what I want to do is I want to explain why hyperbolic groups are, in some sense, the very natural first port of call if you're trying to attack the Boone-Higman conjecture. Okay, either you're just going to find a process that does everything. You assume that you've got a group with solvable word problem and your process just kills it. Okay, or you're going to look at classes of groups and work your way through sort of important classes of groups until you have enough structure that you can maybe make a process that kills everything, right? So if you're doing the second approach, then there's a reason why hyperbolic groups are like a reasonable first place to go. And so right now, the next part of the talk is going to explain that. Okay. All right. So we've all probably seen talks on hyperbolic groups. I'm going to give an unusual definition in the sense that whenever I see talks on hyperbolic groups, I never see this definition. And that's because we all like geometry, and I like geometry as well, but this definition is not going to be very geometric. Okay, so obviously I'm sinning. All right, but to prepare for that, I'm going to do something which is geometric, and I'm going to talk about Dehn when he began this process. So in 1911, he proposed the word problem as being one of the three fundamental problems for finitely presented groups, as I mentioned before. And he also gave an elegant solution to the word problem for a particular family of groups. Namely, you take pi1 of a surface, I think his first thing was either just the closed orientable surfaces of genus at least 2. I'm not actually sure if he did it for non-orientable in his process, but okay, it's like a double cover, so, no big deal. All right, but anyway, but here's the process that he gave. So here's my surface of genus 2, and if you puncture the surface, you can just remove a little disk, and then you can homotopy back onto this sort of wireframe, which is this wedge of 4 circles, A, B, C, and D, and then the walk around that punctured disk will trace out a path on that wireframe, and the path that you get is this one. It's A, B, A inverse, B inverse, C, D, C inverse, D inverse. Well, okay, it depends on where you start and like what orientation you use, but okay, this is one of the words that you could get. All right, and so the presentation for pi1 of the surface of genus 2 is exactly this group. And okay, there's also this whole theory of one-related groups and whatnot, but I want to talk about why this group was really amenable, not amenable as a group, but friendly towards having a solution to the word problem, okay? And so when the genus of S is greater than 1, you get this presentation, and the presentation has something called a small cancellation property. Now, not this presentation exactly, but something very close to it. And so when you have this sort of small cancellation properties that I'm going to talk about, this enables a very fast algorithm to solve the word problem for the group, okay? And so, why are you not going? There we go, okay. So now the class of groups for which you could do this very fast process, which I'm going to call Dehn's algorithm, became a studied class of groups. But it became a while before Gromov gave a geometric interpretation and generalization of those groups that have a potential for doing a Dehn's algorithm kind of solution. And so he gave this nice geometric thing. And the property that Gromov says is you've got some like properly discontinuous co-compact action by isometries, on a hyperbolic space. And then the class of groups that you get in that situation are hyperbolic groups, okay? And then we're all familiar maybe with the thin triangles definition, but I'm not even going to put anything up on the board about the thin triangles condition. I'm going to talk about the Dehn's algorithm and go back to sort of the roots of this, okay? And so an equivalent definition, maybe the original definition, a group is hyperbolic exactly if it admits a Dehn presentation, which is a finite presentation supporting Dehn's algorithm. That's my definition, okay? A finite presentation supporting Dehn's algorithm. Okay, so the key ingredient for the Dehn presentation is that if you look at the basic relators for the group and you look at how they overlap, they can't share a long overlapping common word, okay? And so what happens is if you have two relators overlapping, they're just a small bit of overlap, and then there's a long bit of word which is not in the overlap. And then if you just take a word which is the identity, then and you walk around the, you could do like this sort of Dehn filling for this word, you can walk around the boundary and there will be a long subword from one of your relators appearing in that boundary walk. And what does it mean to be long? It means longer than half the length of that relator. Because then you can replace that word that you see, which is longer than half the length of the relator, by the rest of the relator written in inverse order and inverted. Okay, and then the word will have become smaller. So then you just rinse, lather, and repeat. Okay, you also have to sometimes, kill a canceling pair or something like this, but basically this is the algorithm. Okay, so we take our word, it's some finite string, and the generators are inverses. The word is equal to 1 in the group, and we cyclically reduce it, and then what you're going to have is, because you have the ability to, you have a Dehn presentation to begin with, there's going to be some subword S sitting inside your word W, and there's going to be a relator in the relators such that the relator looks like S times T. Now I'm putting a very forced form on my S because I'm putting in the beginning of the relator. But remember that if a word is the identity, then you can conjugate it and rotate it, and you can just sort of put the substring at the beginning. So you take every relator, do all of its rotations, take every relator, invert it, do all of those relations, and this is your set of relators that you like, okay? Assuming you have a nice beginning set of relators. And then you can make sure that this overlapping part was happening in the beginning, and then that S is greater than half the length of the relator. So now, instead of writing USV, we're going to write UT inverse V, and now this word is now shorter, okay? And so you can like cyclically reduce this thing as well, because I don't know that U or V or maybe they're empty, maybe T's at the end, maybe there's a cyclic reduction is now possible, or maybe at the ends, maybe just a free reduction. It doesn't matter. You reduce that, and you now have a shorter word. So you just keep doing this. You'll stop obviously if the word is empty, and if the word is not empty, you go back to step 1. Okay. And as long as your word really was equal to the identity, you'll be able to find this S. So the real key part here is that there exists this S in this R. Okay. Now what happens is if you think you have a Dehn presentation, if you have a Dehn presentation and you have a word which is not the identity, you won't be able to find an S and an R. You'll have to stop there, and then you'll say, oh, my word is not the identity. Okay. So this is all right. So Gromov claimed in 1987 and gave like a heuristic sketch, and then there's this paper by Olivier in 2005 with overwhelming probability a random group, and there's different kind of ways of arranging the presentation. So a random group in the few relator model with various lengths is hyperbolic. So basically you just wait till the presentation, the relators are getting long, they don't interact with each other very much, and then your group ends up being hyperbolic. Okay. And so, so hyperbolic groups, in some sense, these are groups that have this really fast algorithm. Oh, yeah.
Yeah, but there's a bunch of different statements in the paper, and I pulled this one out.
So this statement is actually obvious. You have to wait until it doesn't matter. The group is not cancellation group. So this is not what Olivier did.
Okay, anyway, I've got this out of Olivier, and actually, I think I got it out of Olivier because you told me to look at the paper, not you, Olivier.
The statement is obvious.
Okay, fine. All right, so I have the wrong paper. I apologize. So I should probably update the slides and talk about Suschanskii more, but you could probably almost always say, right? So I feel bad now. All right. So anyway, but my point here is that what is this Dehn's algorithm telling us? It's telling us that we have an algorithm which is like linear time in the length of the word to solve the word problem, right? If you have a Dehn presentation. So these are not just words with solvable word problem. These are hyperbolic groups are not just groups with solvable word problem. They're groups with a really easy to solve word problem. So in this sense, they're like the first port of call. If you're going to try to verify the Boone-Higman conjecture, why not take the groups with the easiest to solve word problem and say, can I just at least get these? And the answer is yes, you can. So, so if you go and you look, what is this key ingredient that I talk about? It's this small cancellation procedure. So there's a bunch of different rules for small cancellation. So here is the one relator group for the surface. And I actually spoke about how to do this, but I'm going to take my candidate relator in this case,
And this is a presentation which is near to a Dehn presentation for this group, right? No one's telling you like, how do you find a Dehn presentation for a group that's hyperbolic? Okay, you can do it. It's really like not actually that trivial. It's a bit of work, and you have to use like how wide are bigons in your hyperbolic group and all sorts of things to do this. But okay, but let's imagine you have a group that is hyperbolic and that you actually have something like near enough to the Dehn presentation. So this one is near enough in some informal sense. I have just this one relator. So what I'm going to do is I write down all the rotations of the relator. So here I've eaten the first letter, then the second letter, third letter, so on. And you can see the CDC inverse is sort of working its way to the left there. And then over there on the right, I have the inverse of this core relator. And then I'm doing the same thing. I'm eating the first letter and right, I think, oh, actually, I guess, yeah, I'm rotating this the other way. Okay, so it's basically, this row is the inversion of that row. Okay, so here my one relator is length 8. I get 16 different base relators. And then the question is like, how much do they overlap? And once you've done all these rotations, this means that the overlaps are going to occur in the beginning of your relators. All right. But if you look down the first column here, actually every letter is different. And so, I have A, B, A inverse, B inverse, C, D, C inverse, D. So there's no overlaps in this whole column. Okay, but maybe the left column can overlap with the right column. So I want to rearrange things. So I do. And then I discover that I have one letter overlap maximally. Okay, and then I've got 7 letters that are not overlapping at all. And this is good enough. Okay, so there's all these sort of small cancellation conditions, C16, like loads of them. But they're just sort of like generalizations. If you have this small cancellation condition, then you have a Dehn presentation. But Dehn presentations are wider than that. Okay, so let's see Dehn's algorithm in action. So here's just some word. I promise you it's the identity. Okay, that's not very surprising. And so you look for a subword that looks like a big chunk of one of your 16 relators, and we find one. Of course, it's got 7 digits because that's no overlap. And then I replace those 7 digits by a single digit, and now my word's much shorter. And ooh la la, this is actually my core relator to begin with. So yeah, that's empty. Okay, so there's the Dehn's algorithm running really fast. Now I was told that this talk should be also friendly to graduate students. So hopefully that this much is good and you've picked something up if you're in that territory. But I can't promise the rest of it will be all that friendly, but I'll do the best I can. Okay, so okay, this part's still a little bit friendly. All right, so I want to talk about the rational group, which I denote with the script ER. So the rational group is a subgroup of the automorphisms of Cantor space, which we'll talk about shortly. And it was introduced by Grigorchuk, Nekrashevych, and Suschanskii in 2000. This paper has had a really big impact on my life. I spend a lot of time living in the rational group. I mean, I'm normally associated to Thompson groups. I think about the rational group as at least as much as Thompson groups. The problem is I'm always wrong. Right? The rational group is difficult. It's friendly for calculations, and you can build gap programs. We have done that, those calculations in the rational group, but it's a difficult group to study. But the nice thing about the rational group, well, it's got a lot of nice properties. We'll talk about some of them. So, but before I get into them, let me say what they are. So these are the homeomorphisms of Cantor space, which in some very broad sense are finitely definable. Okay, so it's rational in the sense like a rational number is a number that you can describe in a very short, easy way amongst the real numbers. You've got this repeating word in the infinite tail. You just repeat that word forever. So it's a nice finite description. It's easily described. So the rational group in the group of homeomorphisms of Cantor space, this is a monstrously huge group. But there are some subgroups where all the elements are nicely describable in some sort of nice, easy, finite way. And so I don't know that that's actually the motivation for rational. I should ask Elijah. Anyway, so that's always what I thought it was. Okay, but the rational group is not finitely generated, but it is simple. And both these results are by Belkide and Matucci in 2018. And then it's a group that's fantastic because you can embed lots of other groups in it. Okay, so already Grigorchuk, Nekrashevych, and Suschanskii understood that F, T, and V, those Thompson groups are in there. A large group of collaborators with me proved that automorphisms of V are contained in the rational group. It's a really nice subgroup. Grigorchuk's group gamma is in the rational group. And like a lot of these sort of automata groups that we see as automorphisms of a tree, those are in the rational group. And then V gamma, which is if you take Thompson's group V and then you add the Grigorchuk group elements in some cone, then you get this V gamma. This is Rover's group. This is the rational group. And a lot of these sort of simple groups of dynamical origin that Vladi talks about, these are like some kind of generalizations of the Rover construction, which is itself a generalization of Elizabeth Scott's construction. Okay, anyway, everything goes back. These are all in the rational group. Okay, so yeah. So I'll give a proof of that shortly. Okay, so here's an example element. Okay, so the elements of the rational group are given by finite transducers, which you might hear like these sort of Mealy machines, except there's a distinction here, which is that when you read a letter, you might not write anything. So here is an asynchronous machine. So the way it operates on Cantor space, you think of it as operating on the boundary of the tree as a homeomorphism, and the boundary is a Cantor set down there. But it's not an automorphism of the tree because you're not, just getting one letter in, one letter out, and just doing rotations. This is a much, these are not automorphisms of trees necessarily. They can be, but they don't have to be. Okay, and so this thing is finally describable because I have basically two kinds of actions. If I'm on a certain cone or a certain spherical set, I might be acting on that cone the way A acts, or I might be acting the way B acts. And when I say the way A acts, okay, so A, in this case, A is going to be the start state of my machine, and it's going to produce a homeomorphism Cantor space. And so it's injective and surjective from Cantor space to Cantor space, but B is not injective and surjective on a cone. What B does is it takes Cantor space, that whatever your cone is that you're sitting at, and it maps it to some sort of Clopin set in Cantor space, which could be some finite union of cones. Okay, and so, and this particular transducer, so, you can't start, your generator is not A and B, your generator is just A, A. And then what does this one actually do? This transducer does the following thing. If you take the infinite repeated binary tree, and I'm just going to decorate, I'm going to imagine like this machine is like a little spider, and I'm going to put it up here. I'm going to start with A there. And as I wander down an edge, like a 0 edge or a 1 edge, I'm going to travel the same route in the machine. So if I go over a 0, I go to B. So I'm going to put a B at this node. And if I go to 1, I'm going to stay at A, which is, this is similar to the way Grigorchuk's group is acting. And what's going to happen is the cone here is going to get mapped. Okay, so firstly, when I read from A as 0, I don't write anything. But then I carry on and read the Cantor set underneath this address at 0. And what do I write? Well, I write either a 0 and then whatever A does to everything. So that's going to be a whole cone because I promised you that A is a homeomorphism to the Cantor space. So I'm going to write 0 with a cone, or I'm going to write 1, 0 with a cone. So the way B works is it takes this Cantor space and it literally writes, this is what B does, a cone, like a full cone, at address 0, and then at address like 1, 0, so 1, 0, I write a whole other cone. And so the image here is just, it's like a local injection. And A writes the rest. So as I walk down the infinite rooted binary tree, I can decorate all the nodes with A's and B's, and you can think of it as like a little tiling. And here's what the tiles do. What A does is it takes this tile and it rewrites it as that tile. And so you just take all of these tiles that are sitting here that look like, that, and you change the shape of the tree by turning this yellow tile into this tile. And you just iterate that everywhere where an A appears. Okay. Now this is a very friendly transducer because things are not like moving around too much. Yeah. Yes. Okay, so for the rational group, because the rational group are homeomorphisms in Cantor space, it is always the case, right? However, these sort of transducers, they're just defining finitely definable continuous maps from the boundary to the boundary.
and they don't have to be injective, surjective, or whatever. And actually, there's a beautiful part in the GNS paper, the Grigorchuk, Nekrashevych, Suschanskii paper, where they talk about approximating continuous functions by these transducers. And you can just start with any continuous function you want, and you just look at the action underneath a cone, and for each new action, you generate a new state, and you end up with some sort of infinite state transducer. Okay, and if it happens that you only need finitely many states, then that's actually rational. And then if it happens to be a bijection, then that's in the group. Yeah, and it's really a beautiful construction. All right, so the first time I gave this talk, it was, as I was mentioning, at Slava's birthday. So, you know, that was somebody's birthday candle, right? Okay, so anyway, so the rational group is the group where all of the homeomorphisms of the boundary are given by some sort of finite automaton like this. All right, so it's not automorphism of the tree, but like how it's acting on the boundary. All right, so by definition, the rational group that Grigorchuk, Nekrashevych, and Suschanskii define acts on an n-ary tree, and they call that rational group on n. And then they called R2 to be what they called the rational group, and then they showed that all these groups are isomorphic to each other. And the way you do it is a rational transducer that can turn like a 3-ary tree into a binary tree with 3 leaves. Right, and then you can just conjugate by that transducer, and then that will turn the one kind of counter space into the other kind of counter space, and like all is good. Okay, so so I want to think about, like, you know, when we're talking about counter space, I mentioned already that you just build this binary tree, and you imagine that this is an infinite rooted tree, so it just goes on forever, and then the infinite descending paths are infinite words using either 0 or 1 as the digits, and then or as the bits, right? And you just go down and you read your 0s and 1s, and this details an infinite path, and then that infinite path gives you a point in the boundary, and that's a point in your Cantor space. And so you just think of the boundary of this tree. So if this is my tree T2, then the boundary of the tree, that's just some infinite path in 0 and 1. And, you know, I have a beginning and I have an end, so it's 0, 1 to the omega. And then this is like one way to think about Cantor space. And so, you know, I'm going to have this on some slides, so I don't really understand why I'm doing this, but at least I have a picture of the tree. Okay, so this is what I normally call, you know, Cantor space 2. And they're all Cantor spaces when your tree is branching, you know, wherever you are, you can find a branch below and you just descend forever, right? So, all right, so if you go to some location, like you take the 0 edge, then you have the shadow of that vertex, which is this part of your Cantor space. And I call that the branch Cantor space at 0. You also have the branch Cantor space at 1. And, you know, you can carry on. You can keep fragmenting. And in each case, when you keep your fragmenting going on, each one of these pieces just looks like another copy of Cantor space, which is living inside a Cantor space. And so we have a canonical homeomorphism, which is just some sort of like stretching and shrinking linear, like it's an affine map. Some power of 2 will shrink things down and you can translate over. And so these canonical homeomorphisms between the branches of your Cantor space. And so Thompson's group V is the group of homeomorphisms of Cantor space where you're basically just doing these kinds of, you have a finite number of these kinds of maps that are gluing together to fill Cantor space going to Cantor space. All right, so this is one way to define V. But okay, you know, we'll see more of this later. All right, so so anyway, Grigorchuk, Nekrashevych, and Suschanskii say a homeomorphism from Cantor space to Cantor space is rational if and only if it has finitely many local actions. This is the actions on the branches that I was talking about when you just look at what's happening at this branch. And so we should sort of formalize the definition of a local action, but I've already hopefully drawn enough pictures for you to understand what it is. But if you want the formal definition, it's F is the same local action at branch alpha and at branch beta. If there is, if you look at the image of C of the branch alpha under F, that's going to be contained in some sort of like cone, some branch at alpha prime. The image of the branch at beta is going to be contained in some cone at beta prime. And you can look at like the deepest cone that contains the image if you want, and then you get a nice map from Cantor space into Cantor space, and this will be a local injection. Okay. And you just want it so that this following diagram commutes. So the rational group is this sort of really big group, but it is countable because
all the transducers, there's only countably many, right? You have finitely many states, and you just connect them up with finitely many edges. So there's only countably many of these actual functions that you can define. Yeah. What's that? The canonical homeomorphism. All right, so each local action of rational homeomorphism corresponds to a state of its representative minimal transducer. And so like for that original transducer I showed you, there were two different local actions, so we had two different states. And so this is the story. All right, so how do we get the hyperbolic groups to embed into the rational group, right? This is a question. So every hyperbolic group, G embeds into the rational group, and this is a result of Belk, Matucci, and myself. They came out in 2021 in JCA. And the core of the work is to basically use G's action on the boundary. Okay, so you're going to use G's action. So G is a hyperbolic group. It's going to act on itself. And this is going to induce an action on the boundary. But in particular, we need to use the Horner function boundary. Okay, so I'm going to go a little bit through. We have some talks already at a very high level of what is a Horner function boundary. I'm going to just show you how to construct it, right? And so this latter boundary is again a Cantor space, except of course that I'm lying. But it's generally a Cantor space. And if it's not a Cantor space, which could happen, well, you can just take your group G and replace it by G free product Z, and now it will be a Cantor space. And G free product Z obviously contains a copy of G. So, you know, by possibly having some expense of embedding your hyperbolic group into a bigger hyperbolic group, you know, all these lies become the truth. Okay. And so, so it's generally not as easy to work with the boundary. The Horner function boundaries is not as easy to work with as a boundary of a regular tree. So, okay, so I need to talk about something which happens, which is that the trees that we're getting when we're building this Horner function boundary, you know, the boundary is the boundary of a tree, and the tree itself is kind of nice, but not as nice necessarily as these sort of regular two-area trees. We have instead self-similar trees. So here's a self-similar tree. It has two types of nodes. It has the blue nodes and it has the red nodes. And the blue nodes have two children, one of which is blue and one of which is red. And the red nodes have three children, two of which are blue and one of which is red. Okay. And you can just build a regular, well, it's not a regular tree, but it's semi-regular. It's this kind of thing. It's a self-similar tree. And if you have canonical homeomorphisms between cones of the same type, then, you know, we just want to restrict ourselves to choosing finitely many canonical homeomorphisms between those. And then this is the kind of structure that we want. Okay, so the boundary of these things is going to be a Cantor space as long as you have branching, but it could happen that your Horner function boundary ends up just giving you some isolated single edge that just goes forever. And this is why we need to do that free product of Z to get rid of those. Okay. You still have a closed subset of Cantor space, so it would be, you know, compact and closed, but it wouldn't necessarily be a Cantor space, right? So, okay, but anyway, so here is the boundary of this tree. It's kind of weird looking, and it has branches, which are still kind of weird looking, and they don't look the same. I mean, they're the same up to homeomorphism because they have the Brouwer criterion for saying, is it a Cantor space? But they don't have the same sort of geometry the way I'm drawing it anyway, okay? And so, you know, you just keep subdividing into your branches and life goes on, all right? So, so if I take the boundary of my self-similar tree and I look at the space of leaves of this tree, then I'm going to talk about homeomorphisms from that Cantor space to itself. And I'm going to define it just the way GNS did. Sorry, I always call the paper GNS in my mind. Grigorchuk, Nekrashevych, and Suschanskii did. I'll say homeomorphism from that Cantor space to that Cantor space is rational if it has finitely many local actions again. And so then our theorem is, as long as this this Cantor space has no isolated points, which we got rid of anyway when we did the free product with Z, the group, the rational group on the boundary of that tree, that actually is isomorphic to the Grigorchuk, Nekrashevych, Suschanskii rational group on the regular two-area tree. And you can actually do it by taking a transducer which transforms your self-similar tree into like a rooted binary tree in a regular way. And because your self-similar tree is self-similar, you can actually define such a finite transducer to do that. Okay? And so you can conjugate these boundaries. You can conjugate RCT into R by homomorphism. I mean, you would expect this by Rubin's theorem anyway,
But this homeomorphism itself is rational in some sense, but you're going from one kind of Cantor space to a different kind of Cantor space. All right, so how do you build a Hoare function boundary? So you have a hyperbolic graph, like here we've glued together 5 squares, and we just iterate this process. So this is a nice hyperbolic graph. And I'm going to assign some base vertex. And what I'm going to do is I'm going to define the ball at that base vertex. So here are all the vertices that are length 1 away from the origin. Here are the vertices that are length 2, and so on and so forth. And so for each vertex in that tree, I'm going to define this d bar v function. So my vertex is v, and I'm going to define d bar v as you take the distance in the graph from x to v, and you subtract the distance in the graph from x naught to v. And this is the definition that you use for this v. And so what's going to happen is if x equals v, then this is 0, and you're getting a minimal entry there, which is the distance from x naught to v. This is like the most negative you get. And then otherwise, this distance gets to be pretty positive, and that stays constant. So this is, generally a positive function. Okay. And so here is not a hyperbolic graph, but I can still do this Hoare function boundary business. I can still define these functions. So here's my vertex v. It's distance 3 from the origin in taxicab geometry. And if I move v, it's distance 2. And you can see the local minimum is happening wherever I'm putting the v, and then everything else is kind of getting positive far away. And what's going to happen here is, right, if you look here at the ball of radius 1 around the origin, it's 0, 1, 1, minus 1, minus 1. Well, if I look at v here and I look at v there, that ball of radius 1 didn't change in its value. Okay. And so I'm going to define in my Hoare function boundary definition, I'm going to define something called an atom. And the atom is the set of vertices where they have the same values in a ball of radius n around the origin. And so, so we say 2 vertices are equivalent if d bar v and d bar w agree on an n ball. And this is this equivalence classes of this relation are called the level n atoms. So if I start with this tree and I look at all the things that are at the ball of radius 1, I can define this yellow is all the things which are equivalent. They all have the same value, and these are the values on the ball of radius 1. And then I could change to that one, which changes, some of the values here, and I could carry on. And in fact, I have 2 types of atoms, 2 types of infinite atoms, depending on how I set up the values inside the ball of radius 1. Okay. And then I could look at the ball of radius 2. And when I do that, it subdivides, because now I have whatever agreement I had before on an atom. And then because I'm defining more points around the outside on the ball at the shell at radius 2, I get different values. And so my atom that I had is splitting up into different parts. And so I have some sort of splitting of these atoms. And then here's my level 2 atoms, these little intersections that you see out here. Okay. And I'm only going to care about the infinite atoms. All right. So the way that we show that hyperbolic groups embedded in the rational group is we find some, if G's hyperbolic has a finite generating set Y, and you've got the Cayley graph, you look at the infinite atoms, and they have a structure of a self-similar tree. And then you look at the Cantor space of leaves, which you have if you maybe had to do this free product with Z. And so the Cantor space of leaves is a Hoare function boundary. And then there's a natural map from the Hoare function boundary onto the Gromov boundary. It's a finite Terry quotient. And anyway, if you want to look at isometries, say of the visual boundary, these are going to act as rational homeomorphisms in the Hoare function boundary. Okay. And so, isometries of the Cayley graph act as rational homeomorphisms on the Hoare function boundary. Okay. Now, this last part 3, it's tricky. And in fact, for this algorithm, for the proof that I'm giving, sort of the fact that the infinite atoms have a structure of a self-similar tree, and the proof that the isometries of the Cayley graph act as rational homeomorphisms, these strongly depend on hyperbolicity. And there's a lot of geometry in those arguments. So if we wanting to generalize this process to other kinds of groups, you have to get around that obstruction. Okay. All right, so, and of course I mentioned we may have cheated by passage to G free product Z. Okay. All right, so like working with Hoare function boundary is not easy. I've got 30 seconds, but I'm going to be at least 1 minute longer than that. So working with Hoare function boundary is not easy, but this is Davide Perigo. He's just finished. He's a student of Jim Belk and Francesco Matucci, and
he put on the archive his thesis, which develops geometric tools to make it much easier to work with atoms. And he also explores the sort of standard quotient from the Hor function boundary to the visual boundary. So I can, I can suggest this if you're interested in learning the background for this stuff. All right, so here is Grigorchuk's group. This is Bartoldi's picture of the generators for Grigorchuk's group. I don't have 30 seconds, so I'm going to go a little longer. I'm sorry. How do I turn off my thing? Well, I can turn off my phone, right? I can't actually turn off my phone.
Oh, I'm sorry.
But I can make it. I can give my phone to you, and you can turn off my phone. All right, so so what are we going to do? If I take this, one of the things about Grigorchuk's group, and the reason we have this sort of nice intermediate growth, if you look at products of the Grigorchuk transducers at the origin, you just multiply some long word in A, B, C, and D. Then when you pass down into the tree, the local action at deeper cones is involving a shorter word, right, generally speaking. And so this property is called the contracting property. If you descend far enough, your word length is getting shorter. And you can generalize this away from automorphisms of the tree to the groups that we have. So given a self-somewhere tree, we're going to define a nucleus, which is going to be these rational injections. Their domains and ranges are branches on the tree, such that if you take anything in the nucleus, you have to have all the properties that Grigorchuk, like this contracting group, has. So anything in the nucleus, when you descend deeply enough, you're still in the nucleus. And if you're in a nucleus and you're in one of the nucleus things and you descend deeply, then to some whatever length you descend, then you find maybe something else in the nucleus. And if you take an inverse of something in the nucleus, when you descend, then you find something in the nucleus again. And if you compose two things in the nucleus, when you descend deeply enough, you just get one thing in the nucleus. And this kind of structure is already enough to define a contracting property. And it turns out that if we take our hyperbolic groups, it turns out that the generators for the hyperbolic groups in the rational group actually have this contracting property. And it's a miracle, right? So they're not automorphisms in the tree, but they still have this generalized contraction. And so you can just basically use those local actions and build a full group. And if you build a full group, then, so this is like a simple group of dynamical origin, like Villagis stuff and so on. Okay, but when you build this full group, it might not actually be simple. It can be simple, like in Rover's group, but it might not be simple. It has a simple commutator subgroup, generally speaking, but then we've passed, right, the full group contains your group, but maybe the commutator subgroup doesn't. So what do? Well, we have to cheat. And I'm going to just skip ahead a little bit. Here's where the miracle occurs. And when you're hyperbolic, then your tree of atoms, you have this tree, you have the rational realization of your hyperbolic group. It's got this contracting nucleus, and it has all the properties that you need for getting us the full group to be finally presented. But it has two further weird properties. One is that if you take an infinite tail class that's rational, and you look at those words in the Cantor space, and that's dense. And if you look at the group acting on that, you get a faithful or oligomorphic action on this set. And not only that, the action of the full group on those words has finally generated point stabilizers for that. And this is enough to use this miracle theorem of Zaremski working off of work of Belk and Zaremski, which is that if you have a finite presented group acting faithfully and oligomorphically on a set S, and a stabilizer in G of a finite subset of S is finitely generated, which we still have, then G embeds as a subgroup of a finitely presented simple group. And this is a really weird group called the twisted Bryn-Thompson group. This is a higher dimensional Thompson group where you use the action on S to permute the dimensions of your cubes. And so this is a really nice family of finitely presented simple groups. And guess what? They all contain the hyperbolic groups embed into them. And this is our theorem. Okay, so, thanks for your attention.